Hello everyone and welcome back to Math Made Easy. In our previous lectures, we started numerical differentiation for equally spaced data. We learned the forward difference, backward difference, central differences, or higher order different derivatives. But what happens when our x values are not equally spaced? For example, if I take this 1, 1.2, 1.5. So notice that intervals are basically this 0.2 and 0.3 and they are not equal. So we can directly apply the standard finite difference formulas that require a constant h. And so today we'll learn how to find derivatives at unequally spaced points using the Newton divided difference interpolation polynomial. So let's just recall our central difference formulas as is f dash xi approximately equals to fi plus 1 minus fi minus 1 divided by 2h. So this formula assumes that the points are actually equally spaced. So for instance, if I take this 1, 1.52, so that there will be h that is equals to 0.5 and that is perfect. But suppose our points be like 1, 1.4 and 2. Now the spacing becomes this 0.4 and zero point 0.6. So there will be no single h. And therefore the standard central difference formula can't be applied directly. And so we need another method. So idea is actually quite simple. Instead of using the finite difference formula that requires the equal spacing, we all first construct our interpolation polynomial through our data points. And because the points can be unequally spaced, so we use the Newton divided difference interpolation polynomial. And once we have that polynomial, we can definitely differentiate it. So the process becomes this: we started with the unequally spaced data, then we have this divided differences, and then interpolating polynomial, and hence you need to differentiate it. And this is the basic key idea of the today's lecture. So just recall the Newton divided difference polynomial as this Pnx equals to fx naught plus x minus x naught f of x naught comma x1 plus x minus x naught x minus x1 and f of x naught comma x1 comma x2 and up to so on. For the 3 points, we can take this as P2x. And the divided differences becomes this f of x naught comma x1 becomes this f of x1 minus fx naught divided by x1 minus x naught. And this f of x naught comma x1 comma x2 becomes f of x1 comma x2 minus f of x naught comma x1 divided by x2 minus x naught. And the important point is that no equal spacing is required here. Now comes the main step. So suppose you have taken this P2x as fx naught plus x minus x naught f of x naught comma x1 plus x minus x naught into x minus x1 times f of x naught comma x1 comma x2. Now you just need to differentiate both sides. The derivative of the constant term is 0. The derivative of x minus x naught is simply 1. So for the product x minus x naught and x minus x1, using the product rule, need to differentiate it and it will be like this 2x minus x naught minus x1. So this p2 dash x becomes this f of x naught comma x1 plus twice of x minus x naught minus x1 times f of x naught comma x1 comma x2. And this gives an approximation to f dash x. So basically this f dash x becomes approximately p2 dash x. And this is the fundamental idea behind this numerical differentiation at unequally spaced points. So now we have a question here where we have given this tabulated data where this x values as 1, 1.5 and 2.2. And fx as 2, 3.25 and 5.84. And you need to find this f dash 1.5 now using the Newton's divided difference method. So firstly, you need to calculate this f of 1 comma 1.5, which is basically this 3.25 minus 2 divided by 1.5 minus 1, which is basically 1.25 divided by 0.5 as 2.5. And next comes this f of 1.5 comma 2.2, which is basically 5.84 minus 3.25, divided by 2.2 minus 1.5, which is basically 2.59 divided by 0.7, and hence becomes this 3.7. And hence it becomes the second divided difference as this f of 1 comma 1.5 comma 2.2, which basically becomes f of 1.5 comma 2.2 minus f of 1 comma 1.5 divided by 2.2 minus 1, and therefore it becomes as 3.7 minus 2.5 divided by 1.2, and hence gives 1. So our derivative formula becomes this p2 dash x as fx naught comma x1 plus twice of x minus x naught minus x1 times f of x naught comma x1 comma x2. So here we can see that this x naught is 1 here, x1 as 1.5 and x2 as 2.2. And we need the derivative at x equals to 1.5. So this p2 dash 1.5 becomes 2.5 plus twice of 1.5 minus 1 minus 1.5 multiplied by 1. Now this p2 dash 1.5 becomes this 2.5 plus 0.5 and hence approximately equals to 3. So the estimated derivative is 3. Now notice something important. Basically our x values were these 1, 1.5 and 2.2. So the spacing was 0.5 and 0.7. So they were not equally spaced. But we are still able to calculate the derivative. And that's a major advantage of using the divided differences. So for our general Newton divided difference polynomial, this Pnx becomes this fx naught plus x minus x naught times f of x naught comma x1 plus x minus x naught into x minus x1 multiplied by f of x naught comma x1 comma x2 and up to so on. So we can differentiate the polynomial to obtain this f dash x as approximately Pn dash x. And the exact expression becomes longer as the number of data points increases. But the procedure always remains the same. Firstly, you just need to construct the divided difference table, write the Newton divided difference polynomial, differentiate the polynomial and just substitute the required value of x. And that's our general method. Now we can also calculate the higher derivatives as well. And if we have the Newton interpolation polynomial as this Pnx, then this f dash x becomes approximately this Pn dash x. And this f double dash becomes this approximately Pn double dash x. So the same interpolation approach can be extended to higher derivatives as well. So for example, if I take the 3-point polynomial as this P2x, which becomes basically f of x naught plus x minus x naught f of x naught comma x1 plus x minus x naught into x minus x1 multiplied by f of x naught comma x1 comma x2. So we already obtained this p2 dash x as this. So you just need to differentiate once more. So this p2 dash x becomes this twice of f of x naught comma x1 comma x2. And therefore this f double dash x becomes approximately twice of f of x naught comma x1 comma x2 for this quadratic interpolation approximation. Now let's just make the final comparison as is equally spaced data versus the unequally spaced data. As we have in the case of equally spaced data, we have this x naught plus h, x naught plus 2i's of h and up to so on. So we can use the finite difference formula. But for the unequally spaced data, where the intervals are not constant, we can use the Newton divided difference interpolation and then differentiating the resulting polynomial. So let's just summarize what's happened today. So if the points are unequally spaced, you just need to construct the divided difference, form the Newton divided difference polynomial, and hence differentiate it and substitute your required x values. So the key formula for this quadratic approximation becomes p2 dash x. And hence here this p2 double dash becomes this twice of fx naught comma x1 comma x2. So the biggest takeaway is that this unequally spaced data leads to Newton divided difference and hence you need to differentiate it. And that brings us to the end of derivatives at unequally spaced points. And we today we learned how why the standard finite differences formula can't be directly applied to unequally spaced data, and how Newton's divided difference interpolation polynomial allows us to calculate the numerical derivatives. And we also solved a complete example and saw how the same idea can be extended to higher derivatives as well. So with this, we have completed the numerical differentiation in our roadmap. First derivative, higher derivatives, and hence unequally spaced data points. So in the next lecture, we will move forward to the numerical integration, beginning with the Newton-Cotes formulas and the trapezoidal rule. So if this lecture helped you, please like the video, share it with your classmates, and subscribe to Math Made Easy. Until next time, keep learning, keep questioning, and keep practicing, and I'll see you in the next lecture.